That's not. Is it recording? No, it's not recording. Yes, it is recording. Hey, cool. How amazing is that stuff? And now let's see if we can go over to share the screen. What do I want to share with you? I want to share this one with you. Oh, look at that. Ha. What happened? What happened, Edith? I know, yes. And I have all the videos are on Kent Player. There have been some issues with YouTube. So at the moment, the lecture recording playlist is not necessarily be available, I'm afraid. So, and Dari, yes, it's 2 hours, and the first hour is enzymes, and the second hour is statistics. And I don't think it can get any more cruel than that. Thank you very much, Bernardo, for the link. As always, that's very much appreciated. That's cool. And now I want to see if this actually works, what I'm going to do here. So hopefully this is all okay. So let's see. That's especially for Daria, because it's not going to be so bad today, I promise you. And if you can see the smiley face, then I think the setup should work and everything should be fine. Can you see the smiley face? Good. Lovely, lovely, lovely. Excellent. I keep an eye on the time because I am planning to have a little bit of, yes, I'm planning to have a little bit of a break in between. Now it's 2 brows. And let's remove this thing. Ha! Yours is much better than mine. Yeah, I mean, break a leg. Mind you, that is what artists say when they perform, isn't it? Right. And let's keep everything crossed that today we don't have these issues with Teams that we had yesterday. I think I figured out what the problem was, but you know, I'm not entirely sure about that. Okay, are we ready to rock and roll? Fantastic. Okay, so what we have done so far in this module, we discussed this weird Michaelis-Menten equation. Let me write it down again. V equals Vmax times the substrate concentration divided, oh, my lines are a bit wonky, Km plus the substrate concentration. And that is really an equation that you absolutely 100% must know. And I totally insist on that. So I'm sorry, that's something anyone has to know. We said we can draw this a plot here where we plot the rate of the reaction dependent on the substrate concentration. And what we would get is a curve like that. And from this curve, and unfortunately it is a curve, we can't really determine a lot of the essential enzyme parameters. And I told you we have Vmax, we have Km, and we have Vmax over Km. And by now you know what they mean. Vmax tells us when how the enzyme behaves when the substrate concentration is very, very high. Km tells us about the affinity of the enzyme for a substrate. And Vmax over Km. Vmax over Km tells us how the enzyme behaves when the substrate concentration is very, very low. And I think yesterday I showed you how we can actually linearize this equation. And I've given you two different forms. One is this Lineweaver-Burk plot, but don't worry, I'll come back to that. And the other one is what is called an Eddy-Hofstee plot. And again, we will discuss these two forms today. The good thing today for me is that I am on my PC with the sound turned off, so I don't have to worry about any distractions. That's really good. Okay, so now one of the big questions is Microsoft Whiteboard would not do anything because you would not have the annotation allowance from me because I don't want everybody to write on the screen while I'm writing. So that is at least my understanding. Exactly. Anyway, so how do we actually measure these rates? I hear you asking, how do we measure enzyme rates in a practical setting? Because that is what we are going to do. So, right. Now, let's see what we can do in order to measure rates. Let's say we have a reaction where we have a substrate. So here's the substrate. And this substrate is turned into a product with the help of the enzyme. And what we could do is if we could measure our substrate in a spectrophotometer, we could easily find out how quickly the substrate disappears, right? And that is exactly what people do. They either measure the substrate, so they either measure the disappearance of the substrate, or they measure the production of the product in a spectrophotometer per time unit. So how does that look in reality? For that, let me see if I can quickly go over to a different screen. And I think we need to, let me see, screen share. And I need to go over to this screen. Can you see this new screen now? Okay, so now let us assume we have a substrate that we can measure in the spectrophotometer. And what we want to do is we want to measure the rate, how fast this substrate disappears. And this is actually a practical that you are going to do either online or perhaps in person. This will be in week 23, so shortly before we break up. But this is actually how it would work in the lab. What we are going to measure is how fast our substrate disappears depending on the time. So let's choose a substrate concentration. Let's say we choose, well, let's choose 10 micromolar of substrate concentration that we have. And let's start our reaction. It can be either. It can have a color. We just need something to measure in the spectrophotometer. So we start our reaction. We press the start button, which starts the timer and also the reaction in the spectrophotometer. So let's start. So what you see is here the time, and here how the substrate is actually used up. And what we usually do is we take certain measurements in time and write down what the absorbance is. So let's say we measure every 5 seconds. So 25. At 25, we have 731. At 30 seconds, we got 708. At 35, we've got 684. At 40, we got 661. Did you get that? How I did it? So we have to actually have to look at the timer and at the spectrophotometer at the same time. And after, let's say, 5 seconds, 10 seconds, 15 seconds, we measure. Let's do it again, okay? It's incredibly intense. Let's say, yeah, let's do 10 micromolar again. Okay, so we measure every 5 seconds and I shout out every 5 seconds what the spectrophotometer actually shows. And it is going down at the same rate. Absolutely right. Okay, are you ready? We start at 5. We start and then 5 seconds. So I count down 3, 2, 1, start. 4, 5, 828. 804. 780. 757. Did that make sense? Oh, you have to do it. Well. Now, in a real lab setting, this is what you have to do. You have to measure it every 5 or 10 seconds. Right? But because I'm a nice person here in the online version, I have a check your results section and look at that what I've produced here. The spec produces these readings, and modern specs actually will do that. They give you a printout. Does it ever go to 0? Very good question. We hope not. And I come back to that in a minute. So what I do is I just simply copy this list here, And then I change my screen again and go over to Excel. And we are going to analyze that. Hang on. Can you see the Excel screen again? Yeah, wonderful. So let's just simply copy the data that I have just obtained. Let's just simply copy the data in here. Look at that. How beautiful is that? So here I've got my time in seconds, and we have done every 5 seconds. I've shouted out every 5 seconds, but that was just arbitrary. I could have just as well, I could have just simply said we do every 10 seconds or every 8 seconds or something like that. Oh, you don't have to produce, you don't have to write down these numbers, God no, because you will do this experiment anyway. So let's beautify this a little bit. And I want the numbers really nicely in the middle of the cell. So in Excel, I just simply go here to this thing, and I've got them nicely in the middle of the table. So now let's look at, ideally it would be if we could do it face to face, yes, in week 23, but we need to see how the situation develops. If not, you will do this practical online with what I just showed you, basically with this website that I've set up. But I'm not giving you the link to that website at the moment because we are not ready. Okay, so let's have a look at this time course that we have here. How are you going to do a time course in Excel? And that is actually what second-year students currently do in what we call the mini project. So first of all, I highlight both columns. I keep my left mouse button pressed and highlight it like that. Okay. Then we go to Insert and we go to Charts over here. And here it says Insert Scatter. Can you see that? Insert Scatter XY or bubble chart. Can you see that? Excel has another function in it, which is called the line chart. Hands off. Hands off line charts only go for scatter. Okay, so let's do a scatter plot. Oh, look at that. This is a beautifully linear plot. Can you see that? The dots really line up quite nicely. Of course, what we need to do is we need to label the axes, and you have done that already for BI301. So you know how to do Excel plots, right? Am I correct in this assumption that you know how to do these plots? Fine, then I don't have to go through that. You know how to do the axis labeling. You know how to label axes? Brilliant. So here we've got a time course, and what we want to figure out is the rate. So what we actually want to figure out is the gradient. It is absorbance, this one here, per time. And how do we figure out the gradient for this line? There are two ways. First of all, we can produce a line of best fit for these data. You know how to do a line of best fit in Excel? Some people say yes, some people say no. That is the trend line, exactly. So what you do is you choose one of the points, it doesn't matter which one. So you left mouse, click on that. So you've got all the data points selected. Then you right mouse click and a new window comes up and you find here add trend line. Can you see that? Here is the add trend line. So let's click on that. Here we've got the trend line. And what we are interested in is a linear trend line. Do not use these other trend lines. There are massive problems here if you use other trend lines. Go only for linear trend line. And what we want to do is we want to see the display, we want to see the equation for this trend line on the chart. And we also want to display the Pearson correlation coefficient, so the R squared value, because that tells us how good the correlation is. So we just simply tick the boxes here. So what do we get? We get here our trend line. And this first value, so we have y equals mx plus c. And here is our Pearson's correlation coefficient. And we know that, well, it's very, very close to 1. That means a very strong positive correlation. Does that make sense? We see here our gradient. And actually, we don't need to let it go through the axis because the information that we are really interested in is just the gradient, because the gradient, this gradient is our rate. So this is the rate. Let me write this down. Rate we had a substrate concentration of, I think it was 10 micromolar, if I remember correctly. Was that right? 10 micromolar? We got the rate of 0.0047. So 0.0047. And we would see this as the absorbance per second. Okay, so that is our rate for this substrate concentration. Are you happy with that? Actually, it's always a good idea to plot this graph like I have done. Obviously, you would have to do the axis nicely. You would have to label the axis. And you would have to give it a title, but since you've done that, that's not a big problem. So for your experiment, you just simply collect the data and you produce this graph. And it's really important that you produce this graph to see whether indeed it is a straight line, because there are a few things that can happen actually in real life in an experiment. And here is, yes, here, this is the gradient. That's the first value for this straight line y equals mx plus c, and we are interested only in the gradient. The y-intercept we don't really care about. We don't need that really. The gradient is the rate. That's the important thing. And that is the equation for this particular data set. Okay? Right. Why didn't I use the minus sign? That's a very good question. We usually, as I said in one of the previous sessions, we don't care very much about whether it goes down or up. We just simply, realistically, we measure speed in this case. So we just simply say, we call it rate. We look at the disappearance. You're absolutely right. It should be negative, but enzymologists don't like negativity in their lives, and therefore everything is positive. Okay, makes sense? So what could happen in real life where we need to be aware of? So let's draw. Where does this come from? Let's just simply draw two cases that we occasionally observe. So here is the absorbance, and here is the time. And what we are looking for is this straight line in an experiment as here. But what can happen, and very often if people who are new to that, to these kind of measurements, what lots of people will observe is something like that. So you have a straight line here, and you have a straight line here. You've got two straight lines where there should be only one. So what is happening? So at the beginning, our rate is slow. That is what this part here means, slow rate, and then we have a fast rate. So we have slow and fast. What do you think could have happened in this case? At the beginning, it's slow, and then it picks up. Inconsistency, I like that. Inconsistency, but it's not temperature. It's not the temperature, not the pH. It's not the volume. One more. Yes, you're absolutely right. It is a mixing artifact. We haven't mixed properly the enzyme with the substrate. We haven't mixed it properly. So the enzyme doesn't see a lot of the substrate, but give it a little bit of time, then the sort of due to Brownian motion, things get better mixed, and that's when we see a fast rate. So this is a mixing artifact, and we need to be aware of that. So if we see something like that, we can't really use it. What we can do is we can say, okay, we can more or less ignore this part and just simply work with this linear part here. But that's not at the beginning of the reaction, so we need to be a little bit mindful of that. Absolutely right. You miss the starting point, but in a way, it doesn't matter because you try to interpolate from where it is a straight line. And it is a straight line well, I will do a video about that. Let me just say, at the beginning, it will be a straight line, but let's come back to that because that's another thing that you can observe, or that people frequently observe. So here we've got absorbance, here we've got time. And now I need to really pull myself together to get this nicely done. This is another very common observation that people make. So at the beginning, we have a nice straight line. So good straight line. At the beginning, so we can easily measure our rates here, but then we see it sort of plateaus off. Does that remind you of any equations and any kinetics that we have done for that? Well, what do we get when we have a first order? What do we get when we have a zero order? It could be second order, it could be first order, it could be anything but a zero order, because a zero order, that is actually what we observe here. This would be a typical zero order, but this here is anything but a zero order. It it plateaus off here, probably goes down a little bit further like that. What's happening here when it plateaus off? What happens here? Before we had the mixing artifact, and here it just simply means, is it frozen? Well, yeah, that's a good thing. What actually happened is we are running out of the substrate. The enzyme has basically used up more or less all of the substrate, or can't find the substrate. So we are no longer at a good speed here. And Ellie absolutely nails it. Yes, that's pretty much what we see. We are running out of substrate. But actually, this isn't such a big problem, because all we need to do is we just simply say, right, we don't need to measure this part down here. All we need to measure is this part here, where we are still a nice straight line, where it is still straight, and where we can get the gradient for this line here. So we get the gradient for that. All we need to do is just simply ignore this part here, where we are running out of substrate, and just use the data for the first part. Does that make sense? So these are the artifacts that we could encounter, or very frequently encounter, when we do these measurements. Right, and obviously what we need to do is, if we want now to find out our enzyme parameters, what we need to do is we need to measure, we need to do the same thing. We need to do the same procedure, not just for 10 micromolar, we need to find the rate for all the other concentrations that we are dealing with, because we need that for our Michaelis-Menten plot or the other plots. So because I'm a nice person, I have done already some measurements, and I've converted the absorbance into micromolar per minute. We know how we can do that, just simply by using the Beer-Lambert law. We can convert absorbance into a concentration. And we have done that in the BI301 module. So here we've got substrate concentrations and the rate. Now let's see if we actually get, with these data, if we get a proper Michaelis-Menten plot. So again, what I do is I highlight it, I go to insert, I do my scatter plot. This time I want to do it really nice with a curve, sort of, and look at that. Isn't that a beautiful plot? So here I just quickly do the axis labels. Here we've got the substrate concentration. So S, and that was in micromolar. And here we just simply have the rate, and that was in, what was it? Micromolar per minute. Here we've got everything nicely laid out, and that would be here a Michaelis-Menten plot. Plot. This is not a line graph. This is still a scatter plot, but I used, let me go back to that. This is still scatter, but it allows me to put in a line that connects the dots. Either way is fine. Just in this case, it makes it look nicer. But you're right, I probably should do something like that. Okay, so this is our Michaelis-Menten plot. Now tell me, what do you think is Vmax in this case? Can we find Vmax? 90? Are you sure? How sure are you that it is 90? Around 80? You see the problem that we have. You see the problem. Some people say 80, 85, 90, and depending on what your estimate for Vmax is, it will also then impact on Km, on the affinity. Just simply because we need Vmax, because we need to find half of Vmax. So if it was 90, if Vmax was 90, if this was the line where this curve was converging to, then our half Vmax would be 45, and we would get this substrate concentration here, right? For 45, we would probably get it something here, 50 micromolar. If it was, let's say, 100, then it would be higher than that, our Km. So you see the problem. We can't estimate Vmax. And if we can't get Vmax, we can't get half of Vmax. And if we can't get half of Vmax, we can't get Km. Right. So how do we deal with that? let me just simply copy these data. And I put them in like that. There are a few numbers too many, but that's not a problem. We just simply remove these extra numbers. Oh, we got the same number here. So what we can do is we can now try our linearized plots. And remember, yesterday I showed you one of the linearization, the Lineweaver-Burk plot. So, and in this Lineweaver-Burk plot, we calculate 1 over the rate versus 1 over the substrate concentration. And what we get is, we should get a straight line. Okay? Now let's do that. So let's simply do this calculation here. So this would be 1 over the substrate concentration. And here we would have 1 over the rate. So all I need to do is take this value here and calculate 1 over, what's 1 over 5? One over 5, 0.2. What's 1 over 8.3? .12. Now I'll tell you what, I'm really too lazy to do that by hand. So what I'll do is I will put in an equation. And every equation in Excel starts with the equal sign. Equals 1 over the value that I have in this cell. Ta-da! And I do the same thing for 1 over V, but let's do the calculations for this one here as well. So I could do exactly the same thing, but actually, to be perfectly honest, I'm too lazy to do that. Because Excel can do that for me. So I highlight the cell. You see the cell highlighted, and here's the equation. And look at the corner of this cell. Let me make this a little bit bigger. Right? Look at the corner. You see this blue dot here. Do you see that? Yeah. Now, what you do is with your mouse cursor, you go onto this blue dot and you see it changing. You see a black hair cross turning up. Keep your left mouse button clicked and drag the cell down. Wow, it does all the calculations for you. How cool is that? Now we can do the same thing for 1 over V, but actually, to be perfectly honest, I'm too lazy to do that because what goes in the vertical direction also works in the horizontal direction. So we can take the mouse cursor and drag it sideways. Look at that. We get our data easily calculated. Is that cool or is that cool? Excel is power, indeed. Now let's do a plot for that. Okay, that's our plot. And let's insert it. And again, we go for scatter And oh, cool, look at that. Here we get our, no, it doesn't do. That's a very good question, actually. Thank you for asking. So here we've got the reference equals 1 over B36. So that's referencing this cell, right? B36 is this cell here that we reference. But now check out what the reference is when we drag it sideways. Do you see what the reference here is? It's now this cell. There is a way, if you don't want this to change, there is a way to fix it, but I'm not showing you that, not now. Now look at our beautiful Lineweaver-Burk plot here. So we've got data points here. Shall we do a trend line? Yeah, because it's so easy. So let's do the trend line. Here is the trend line, display the R squared and display the equation on it. So here we've got an almost perfect match. R squared is 1, so that's really good. And we've got the equation for our line of best fit. So here, y equals mx plus c. And now we need to really remember, what was this mx plus c? Now in the Lineweaver-Burk plot, we said we have 1 over v equals km over v max times 1 over s plus 1 over v max. That was what we developed yesterday. So this is here y equals mx plus c. And the c, that's our intercept. That's this number here. That's our c. So c, that is 0.01, and that is 1 over v max. Did you get it? So what is v max? What is v max in this case? Indeed. To get v max, we just simply calculate 1 divided by 1 over v max equals 100. And the units here would be micromolar per minute. Hey, cool. How do we find Km? Well, actually, what we could do is we could use that. We could use this value for Km over V max. So this is 0.55. So we have Km over V max. That's our gradient. That's 0.55. 0.55. We know that V max equals 100 micromolar per minute. So what we need to do is we just simply say for Km, would be 0.55 times 100 equals 55. And because we were really sloppy with the axis, in this case, it would be 55 micromolar. You see, we can very easily calculate from this plot the data that we need here. Are you happy with that? This is how you do a Lineweaver-Burk plot. I have videos on the playlist that shows you how you do that actually with an Eddie-Hofstee plot. And the 0.55, that was here our gradient that we get for this trend line. So I promised you a break before we head over to the BI308 and where we do a little bit of statistics. So I hope you enjoyed that. And that is actually something that you will do. These kind of plots is what you are going to do quite a lot when you go into your second year and probably even in your final year, where you measure enzyme kinetics. We will go through the different plots again in one of the subsequent lectures, but here you got at least the gist how this is done. So thank you very much for watching, and we are then going over to BI308, which will start at 5 past 12 over on the BI308 channel. Thank you very much, and see you in 10 minutes time.